Alright, so you guys have titled your notes Transforming Sine and Cosine. Transforming, the graphs of sine and cosine. So the first thing we have to go back to is transformations. So if we think about all the transformations we can do with a function, we've got kind of left, right stuff. So if you want to go left or right, f of x becomes f of x plus or minus some number. That's how we go left, right. If you replace x with x plus 5, you're going to go left 5. If you replace x with x minus 2, you're going to go right 2. So this whole left, right, that was a replace x with x plus a number. That'll take you left or right. Left. I guess if it's x plus a positive number, it'll take you left, or x plus a negative number, that'll take you right. Nonetheless, you got left and right. Replace x with x plus or x minus something. Okay, we have the next one was up, down. So f of x becomes f of x plus or minus some number. This was add some number to the end of your function. So f of x plus 6. X squared plus 6. What's the transformation that occurred here? Up 6. All the vertical ones stay true to their sign. It's the horizontal ones that are always backwards. This is up 6. So these rules apply to the trig functions as well. So sliding them left and right, sliding them up and down. So we got left, right, we got up, down. Then we have the stretches. So let's go vertical stretch. So that's going to, what that's going to allow us to do is stretch your waves out like this. We talked yesterday about it's not as if your waves are always, from top to bottom, it's one unit. Okay, if you look at sine and cosine, the maximum of each of them is 1, the minimum is -1. So we need to be able to stretch them. So for vertical stretch, this is number times f of x. That's all it is. Now, if your number is greater than 1, will it make it taller, stretch it out, or will it compress it? Stretch. Yeah, taller. So the vertical ones are always they're always pretty intuitive. So number greater than 1, this is stretch. Now these transformations, do they affect x values or y values? The vertical stretch one. Y values. Yeah, vertical stretch, that's a y values thing. Now if your number is bigger than 0 and less than 1, it's a compression. So maybe your graph started out and it looked like this. And maybe you've compressed it and now it looks like this. Okay, we're almost there. So that's the vertical stuff. So just put a number in front of your function and multiply it. And that's going to have a vertical stretch or compress. Okay. So let's say we want to stretch this thing out horizontally. Horizontal stretch by a factor of 2. If you remember, any time you did anything horizontally, the language we used was always replace x with this. Replace x with this. And the vertical stuff was always do this to your function. Add 4 to your function. Multiply your function by 6. So if we're replacing x with something, we're talking about horizontal changes there, left to right. If we're doing something to our entire function, that's the vertical stuff. So if you want a horizontal stretch by a factor of 2, this guy here would be replace x with, anybody remember? Almost. Remember, the horizontals are backwards, actually. 0.5x, 1/2 x. And these guys here, if you were doing it with a table, these guys are going to modify x values. So all of the horizontal ones, they're all, none of them line up with your intuition. They're always opposite of it. X plus 4, left 4. 2x, oh wait a second, 2x actually doesn't stretch it out. 2x actually compresses it. So at least they're consistent, but the horizontal ones are always counterintuitive and the vertical ones are always going to be intuitive. Okay, we had one more really set, and those are the reflections. So if you want to reflect over the y-axis, is that more of a horizontal change or a vertical change?
Vertical change. Oh wait, reflect over y-axis. That's horizontal.
Yeah, if you have some shape here and you reflect it over here, vertically it didn't change where it lives, it was a horizontal. So is that a case where you do something to the function or you replace x with something?
Replace x.
Yeah, replace x with. Good job. So this would be replace x with negative x. If you're going to reflect over the x-axis, that's vertical. So whole function times -1. Okay, so now we can actually get into some of the trig. So that was a quick review of transformations. I think all the review you're going to need. All right, so let's say we have sine of x. Say the period of this graph. We talked yesterday. The period is 2 pi. Looks like this. Anybody know what this marker is right here on the x-axis? 4 pi, yep. If it takes 2 pi to do 1 cycle, it takes 4 pi to do 2. So that's up at 1. That's at -1. So there's your basic sine. Well, let's say, what if we had 4 sine of, I don't know, let's go with, we'll go with 4x plus, well, we'll leave it like this. Let's say we wanted to graph this new function. Well, I know how to graph the basic one, and I know about transformation, so I can do this. This is fine. I just have to do it one piece at a time. I think the first thing you need to figure out is, yes, there were transformations. What were they, and in what order did they occur? Right? Order makes a difference here. So, let's start with sine x. So what's the first possible transformation we did to sine x? You guys think it was the vertical stretch by 4, the horizontal compression by a factor of 4, or the vertical shift up 9 units? You think the compression, the horizontal? Okay, so let's say we want to do the horizontal compression. So if sine x is going to become sine of 4x, and that was a h horizontal compression. So our goal is, we're going to start here. We're going to try to build this function. And as we build it, we're going to keep track of the transformations we used. If we can understand the transformations we used, we'll be able to take this graph up here, transform it, and we'll have the new one. Okay, so slide this up. So now the next step, sine of 4x. You want to add 9 to it, or do you want to multiply it by 4 first? Okay, so if you multiply it by 4, you'll have 4 times the existing function, which is sine 4x. What does that do? V stretch, vertical stretch. I don't know if you got lucky or if you just know what you're doing, but it was definitely the right decision to first vertically stretch it by 4, then add 9. Had you done the plus 9 first, your next step when you multiplied by 4, so if you were sitting with, let's say, sine of 4x plus 9, and if you now said, hey, multiply your function by 4, you'd have to multiply your entire function by 4, thus causing the 4 to be distributed here and here, and your vertical shift would have now been 36 instead of 9. I don't want to say you do audit. You build it. You build it first. Keep track of what you're doing, and if you end up with the right result, then go back and retrace your steps. And by all means, if you can figure out a way to generalize it, Anthony, so it's right every time, do that. I just don't want to do that for you because I'll cause more problems than anything else. Okay, so we're almost there. We're trying to match up with the blue. We're sitting right here. So all we need to do is do what? Up 9. So up 9. So 4 sine 4x plus 9. So that's up 9. So we've got the order figured out. This is the first thing. This is the second thing. This was the third thing. 1, 2, 3. Okay, the first thing we do is we horizontally compress by a factor of 4. Does that make it the wave longer or shorter?
Makes it shorter.
Shorter, okay. So it's now shorter. How long did one full cycle used to be?
2 pi.
2 pi.
So 1/4 pi. Half pi.
Yeah, good, yeah.
What the heck am I thinking?
Now tell me your guys' thinking on that, because I think somebody watching this video, it might not be as obvious. You guys said if the original period was 2 pi, the new period is
Half pi.
half pi. What did you do to 2 pi to get it to half pi?
Divided by 4.
Okay, so you did 2 pi divided by 4 is half pi. So what's the period length of this one?
Pi or half pi.
It's half pi. Now, if you remember from the other day, I said you have to make markers at every quarter. So it does certainly finish in pi over 2. Pi over 2 is one full cycle, but break that up into quarters now. So what's the middle going to be?
Pi over 4.
And what's the first? What's this one here?
Pi over 8.
So your smallest measurement there was 1/8 of a pi. So you have 1/8 of a pi plus another 1/8 of a pi is 2/8 of a pi. Plus another 1/8 takes us to 3 pi over 8. Alright, so now you've got the x-axis all figured out right there. You have made the necessary adjustment for the horizontal compression. Okay, now you got to vertically stretch it by a factor of 4. Will these points right here be affected by a vertical stretch?
No.
No, so they're still going to be there. So I had it at the beginning, at the end, and we really should have marked this one out at its quarters. So it would have been here, here, here. Now that vertical stretch is going to affect the peaks and the valleys. How high did the peaks and valleys used to be on the original graph?
1,
So how high are they now?
4.
4, negative 4. Uh-oh. Okay. So if I stopped there, if I didn't have that third transformation to do, so this is without the third transformation, I still got the same basic shape. I'd have that. That'd be one cycle. But we're not done. Duncan, what's the last thing we have to do? Up vertically by 9. Now there's 3 things that I'd move. When I do these, and you can frame it in your mind however you want, but I think of, you've got the top, you've got the middle, and you've got the bottom. Each of those lines has to get moved up 9. So instead of the top being at 4, the top is now at 13. Instead of the bottom being at negative 4, the bottom is at 5. And now the middle used to be at what? 0. Now the middle is at 9. So we said, hey, that guy is no longer 4, that's 13. This guy is no longer negative 4, it's 5. And the middle is now at 9. Now, kind of weird to have the x-axis drawn where 9 is. So if you were going to clean this up, let's say I put that guy in, I'd probably erase that, erase that. I'm going to have to erase this guy. It doesn't have to be a work of art. I'm going to have to put those labels now down on the x-axis. I'm waiting for somebody to ask the question, like, really, we can't just cross out the numbers on the side and put the ones that should be there? I'm fine with that for now. I really am. You get the idea. I don't want to, this doesn't need to be more work than necessary. Now, if I feel like you couldn't do this, I'll ask you to. But it's more time consuming than it is anything else. I really think once you relabel those numbers, I think you understand what you're doing. The picture doesn't necessarily look super pretty, but you got it. You got it. So, how long till we're out? 10 minutes? Okay, let's do one more. This one is going to be a bit nasty, but we're going to do it. It'll be fine. Anthony, question, sir?
Why do you have to label and mark the fourths? Why can't we do like the halves? Why do you need that?
When you think about, so the question was, why do we have to do it on all of the fourths? As far as the unit circle goes, all of the extremes really happen at the fourths. Like if you think about at 0 degrees, at 90 degrees, at 180 degrees, at 270, those are the markers we most often use. There is a lot of stuff in between, but they're actually the easiest ones to use because it's you're either at the middle of the graph, the top of the graph, or the bottom of the graph. Any other questions you guys want to ask about this? It's as much of an art project, I feel like, as it is anything else. Okay, one more. Let's go with cosine. Oh, and let's make this one kind of mean. -3. Let's go -3 cosine 2 pi. No, let's go with 1/2 x plus pi minus 9. All right, one step at a time. So, cosine x. Okay, first off, well, what does it look like before it's just killed by all of these transformations? Well, it looks like this. What makes it different than sine? Well, sine starts at the middle, cosine starts at the top. So we have a basic understanding of what cosine looks like. We'll just tuck that off to the side. Okay. So we got to recreate our function so that we understand the transformations that occurred. So, first transformation, anybody want to take a guess? What's that? Okay, Colin just flip-flopped. He's wondering, does he do the horizontal stretch or the horizontal shift left pi units? So watch this one. If you first go 1/2, if x becomes 1/2 x and then x becomes x plus pi, you end up with that. If x first becomes x plus pi and then you replace x with 1/2 x, you get this variety. So do we want option 1 or option 2? Option 2. Option 2, because we're trying to match up with this one, and that one doesn't do it. So this guy is gone. If we do option 2, did we go left? We went left first, right? That was this guy. So left, how many units? Okay, left, pi units. So cosine x became cosine of x plus pi. Left, pi units. Okay, next, what do we do? We went left pi units, and what did we do to the graph? Good. Okay, horizontal stretch by factor of 2. So cosine of 1/2 x plus pi. So x became 1/2 x. Horizontal stretch. Okay, now you got to decide, are you going to do the multiply by 3 or the minus 9? What do we got? Multiply by 3. Good job. So this guy, we're going to go 3 cosine 1/2 x plus pi. How does that change the graph?
Flip-flops. Oh, you just said 3. Just kidding. Well, it's vertical stretch.
Okay. Vert stretch by times 3. Okay, next, you're going to multiply by -1 or subtract 9?
You're going to multiply by -1.
Multiply by -1. If I multiply my function by -1, I reflect over the x-axis. Very good. Very good. Reflect over the x-axis. Okay, and the last thing is to do what? Subtract 9, which is going to do what to our graph? It's going to go up, down 9? Down 9. Oh, down 9, okay. Okay, so we've got them, and we've got them in order. Now, what I want you to try to do, I'll finish this up, is I want you to actually try to draw the graph. That's your homework this weekend. I'll put my solution at the end of this video. I'll pause it right now. But now that you've got these transformations in the right order, see if you can take the original cosine graph and do it. If it were me and I was in your position and it was the first time I was really doing these, one of these, I would do multiple graphs and it would probably take me, well, I'm messy with paper, but probably one piece of paper. So get it right, take your time, it's one problem. Alright, here we go. So we're going to finish this thing off. So, this is a transformation of cosine x, which normally here's the top at 1, here's the bottom at -1, and it has a period of 2 pi, pi. This guy here was pi over 2. 1/2, 2/2, 3/2, 3 pi over 2. So, just cosine x looks like this. Now we actually have to get through the transformations. So the first thing we did was it went left pi units. Okay, so go left pi units. All these points have to go to the left pi units. So, you know, think about all of these values on your x-axis. They all need to get, you need to take pi away from all of them. So instead of this guy being pi over 2, that one is going to be, let's see, pi over 2, if you want to do this, minus pi. Well, that's pi over 2 minus 2 pi over 2. Oops. So that's negative 1/2 pi. Okay, so we got to shift this thing left half a pi. So, or we said, sorry, left pi units. So, it might be helpful. Let's say we continued the original cosine graph. It's going to go like this. I just want to be able to see one full cycle of this graph, and if you shift the red graph to the left, we're going to be on the left side of the x-axis, which isn't the worst thing in the world. But if I sketch out cosine so that you see more of it, I think I can more easily shift it. So I got to put some markers on here too. So it's good. Normally cosine would finish 2 cycles in 4 pi. So that's kind of the lowest, the smallest chunk we use. So each of these spaces is a half of pi. So you got half pi, 2 halves pi, 3 halves pi, 4 halves pi. The next would be 5 halves pi. So 5 pi over 2. 6 pi over 2, which would be 3 pi. 7 pi over 2. Okay, so this graph has to go to the left pi units. So, let's do just that. So if you take this point right here, and it goes to the left pi units, it's going to be now moved right here. Okay. So it'll get moved over there. I was hoping to do these on the same graph, but it might not be the cleanest thing to do. Okay. So we're going to move this guy first. So if that point moves left pi, it's going to be now on the y-axis. And that's that. I'm going to slide this point over. I'm going to slide this point here over. I got to slide this guy over. I got to slide this guy over. This was my first point that I slid to the left because it's going to end up on the x-axis. So I think that's going to be the cleanest way to do it. Okay, so the point at pi gets shifted left. That's down at negative 1. 3 pi over 2. That guy's got to go left pi units. So 3 pi over 2 minus pi is pi over 2. So that's at pi over 2. So this point is on the x-axis. When it goes left, it'll still be on the x-axis. The next one I have is 2 pi. 2 pi take away pi is still just pi. So at pi, so right here, that's at pi. The y-coordinate of this point is 1, so the y-coordinate of the new point will be 1. Okay. The next point, 5 pi over 2. Well, 5 pi over 2 take away pi is 3 pi over 2. That's on the x-axis, so this guy will be on the x-axis. And you can see from the pattern what this thing is going to end up looking like. Our next marker, well, this thing is every half a pi. So I say this is 1/2 pi, 2 halves pi, 3 halves pi, 4 halves pi. Well, that's just 2 pi. Yeah, this guy here is 2 pi. Okay, so the point that got shifted over was actually this one right here. So if you take pi away from 3 pi, you get 2 pi, and the y-coordinate is -1. And we'll come up with some other strategies for how to be a little bit more efficient here. But the horizontal shifts are definitely the toughest.